Hello, everybody. We are going to work on limits on the recursive sequences. And this is for the calculus part of the course MATH1251 at University of New South Wales. That is question 67. We are going through the solution of it. Fx is defined as a function, and an is a recursively defined a sequence. The starting of the sequence, a1 is 1, an plus 1 defined as this function evaluated at an. Now, we would like to show that f is a monotone increasing function in this interval, and then we would like to show that an is bounded. And since monotone increasing and bounded as a series, then it has a limit. Then we will find a limit. Now, since we are dealing with the sequences and the sequences are indexed by the natural numbers, when we are proving something related with these natural numbers, indexed by the natural numbers, we almost always think about the induction method. This fits perfectly because you check with the initial step works, and then we assume that it is true for K. We call that step is induction hypothesis. Then by using the K step, we would like to prove that K plus 1 step is true. It's all about the induction method. Now let's do the question. Now this green area is, I just would like to recall what it means. So if you have a monotone increasing function, by definition, x smaller than y implies that fx smaller than fy. So this is definition. And we have a test for it. If the first derivative is bigger than 0 is positive in the interval that you're dealing with for all x's in your interval, then it implies that f is increasing in the interval. Now we can use the first derivative test for the function, and this is a quotient rule that we are going to calculate the derivation of this function. So the derivation of 2 will be 0 because it's a constant. So the quotient rule says that to take the derivative of that one, which is 1, times the denominator of x plus 1, minus the derivative of the denominator, which is 1, and upstairs is x minus 1. That's that. And then divided by denominator square, divided by denominator square. Now on the numerator, we have x and minus 6 that cancels out. We have plus and plus 1, that's 2. So this is always a square, is always a positive number. 2 is a positive number. All of them is a positive number. So it is true for any actually real number that is a monotone increasing, that's constantly increasing function. Now, this was the first part. Now, there is a sequence. Since we are defining the sequence with respect to the FAN, and then AN as a function is an increasing function, and for each indices are also representing an increase. So it means that the sequence goes up, 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 up. It means that the AN as a sequence is a monotone increasing as well. Okay, now about the bounded. We need to find out a bounded above. We need to guess a boundary number for above. So this is the thinking part that we are doing here. That's how I wrote it. What kind of number that I need to choose so that I can prove the sequence is bounded above? That's the question. So we need to, I'm looking at some of the numbers in the sequences, which will give me some intuition what kind of numbers that I need to choose for the boundary above, what my guess should be. Of course, I need to prove it, but I need to guess, initial guess I need to do. A1 is equal to 1, A2 is FA1, that will be 2 plus A1 minus 1A plus 1. So this is basically 0. So I have only 2 left. A3 will be FA2. This is 2 plus. Now I am putting 2's here as A2. So that will be 1, that will be 3. So this is 2 plus 1 plus 3. So it is bigger than 2. So I'm going to use the guess that 3. So my initial thinking, my initial guess is AN is bounded above 3. If it wasn't working, if it doesn't work, then I needed to look at back and do more thinking about it, right? That's how it goes. It's a trial and fail in trial and test in trial type of approach. Okay, so I would like to use induction method to prove that AN is smaller than 3 for HN. For initial state, we know that A1 is equal to 1. This is initial step. I need to look at the first step, which is k is equal to 2. A2 will be just 2, as we calculated here, is smaller than 3. That works. So induction hypothesis, we assume that AK is smaller than 3. So this is our assumption. This is the K state is in our assumption. We would like to prove that K plus 1 state by using the K state will be correct. So AK plus 1 by definition is FAK. That is 2 plus AK minus 1 divided by AK plus AK minus 1, AK plus 1. So we would like to show that this is smaller than 3. So let's sort of decompose this with respect to the inequalities. So we have AK smaller than 3. This is our induction hypothesis. So if I take minus 1 on both sides, IK minus 1 is smaller than 2. So this is 1. And all of my sequences are also bounded with 1 because A1 is equal to 1. It is bounded by 1 and it is increasing. So bounded below has to be 1. So this is what I'm saying here. 1 smaller than AK for all K for this sequence. Adding the 1 on both sides, I have 2K and I have AK plus 1. So flipping over will be just making this inequality in bigger sign. Or you can think of you taking this one as a division here and take this one as a division here. Then we have this inequality. So this inequality times this inequality will give us AK minus 1 divided by AK plus 1 is always smaller than 1. So we have 2 here, and we have another number which are smaller than 1. It means that AK plus 1 is smaller than 3. Okay. Now we have our sequence is bounded above, and it is monotone increasing. Then it has a limit. Also, it is bounded below by its definition. Now we would like to find out the limit. Now, in this section B, we show that the limit exists. In this section, we would like to show that what is that limit. So since the limit exists, it should be a number. And let's call this number is L. Limit n goes to the infinity an is equal to L. The idea here is that if we add or subtract a number, a minus 1 or plus 1, or a number, a fixed number from infinity, we still have infinity. Infinity plus 1 is infinity, plus minus 1 is infinite. Even for any fixed number, that is what it is. It's infinite. So A infinite in this case will be is equal to A infinite plus 1. So we will be able to get these equations. So this equation is true at infinity. It is not true for the present, but it's true for infinity because we are saying limit n goes to the infinity an is equal to L. Also, limit n goes to the infinity an plus 1 is equal to L. So this is the an plus 1 limit, and this is the an limit. Right? This is a limit condition, so L is in the limit. So we have an equation and L is unknown, and we can solve this equation. So we have L plus 1 multiply here, L plus 1 multiply here, L square we will have, and we have L in this section, and we have 3L will go to the other side as minus L. We have 2 and minus 1, that will be minus 1 is equal to 0. So we have L squared minus 2L minus 1, and let's calculate the roots of it. And the roots will be 1 minus plus square root of 5 over 2. And this is a number with 1.19. If we take 1 minus 1 over 19, we will find the one of the root is 0.19, and that is smaller than 1, which is impossible. So this cannot be the limit that we are searching for, because an is bounded below by 1 and bounded above is 3. So L1 cannot be the limit. So L2 is 2.19 is around that number, is between 1 and 3, which is quite the positive. So that L, this number, is our limit. So limit n goes to the infinity an is 2.119. So one thing that I would like to remind you here, if we have limit n goes to the infinity an, with this will be like 2, and you will have 1 if you think as a function, and then that will be 3. It looks like a contradiction. So why this is not working? This was one of the questions that I faced with. So this is the explanation. So A2 is 2, A3 is 2, 1 over 3, but A4 is not as 1 F1 over 3. The proposition that you have, if you have a sequence, f is a function defined on this interval, an is equal to fn, for an sufficiently large limit exists, then limit of an is equal to limit of xn. This proposition cannot be used for this case because this fails. Because this is the requirement in order to be able to use this proposition. You cannot use this proposition because it fails. Okay, so this is the one of the questions that I faced with. So that's an explanation of it. And that's all for this video. And thank you very much for listening. I hope it is useful for everyone.